before we get to today's video, which is going to start a new section talking about functions and relations, I just want to quickly mention, in the first couple of videos, and including in this video, I've realized that I haven't done a whole lot of really rigorous set theory proofs that you would expect in an axiomatic set theory course. This will be remedied quite soon. The thing is, a lot of the very rigorous proofs right from the axioms at this point in time are basically stuff that you would have been doing in naive set theory anyways. And the other thing is, I'm kind of selfishly really antsy to get to the meat and potatoes of this course, being, well, one thing I'm excited is talking about the formal construction of the natural numbers, which I will definitely go full painful rigor on for that section. And then the other thing is talking about infinity, dealing with ordinals and cardinals and the strange arithmetic of infinite numbers. So if you just bear with me, the next few videos might not be, the tightest detail of rigor. If you guys, beg me to release some extra content which has some boringly rigorous proofs, I'll do it. I will do it. But just so you know, the extreme rigor, it is coming. This is a little bit further down the line. So with all of that out of the way, you know what it's time to go to, the Platonic realm! Now that we've defined our main objects of study being sets and a couple of the basic operations and properties thereof, we now want to study relationships between sets. Namely, we're mostly going to be interested in functions. But as a step to getting there, we need to make the definition of a relation. Say that a set is a binary relation if all the elements are ordered pairs. So a set looks like some collection of ordered pairs A and B. So all these A's belong to some sets, and all these B's belong to some sets. It'll be common for us, and just in general, to use the notation instead of writing elements A and B in the set R, we will instead write A, R, B, meaning A is related to B through R. Because we're typically thinking about R as being some way to relate the first coordinates to the second coordinates. So we think of R as actually being a relationship between these two sets. And what these sets are in particular, so A is really the collection of everything that comes in the first coordinate. So we write this as the domain of R, which is precisely just all those x, such that there exists a y where x is related to y. And similarly with B, we call this the range of R, and this is just the set of all y such that there exists an x where x is related to y. We also have the notions of image. So the image of a set A under a relation R is simply the collection of all those elements which are in the range of the relation, such that there exists some x in A so that x is related to y. Similarly, we have what's called the inverse image, and this is just the collection of all those things which are in the domain of the relation, such that there exists a y in the set B where x is related to y. We can also define what's called the inverse relation, which is R inverse, and that is simply the collection of all x and y such that y is related to x. So we just flip all the relations around. One thing to notice is, again, I'm being sort of glib here and ignoring in many of these cases the axiom of comprehension, but it's worth taking a moment to think about what set would be here in order to make this properly formal. For instance, in this case, I'll just give it away. It's it would be the range with the Cartesian product of the domain of R. Now I've realized we're a couple of videos into our course on formal set theory and have really neglected to prove any theorems for you formally. A lot of what we've dealt with so far more or less boils down to naive set theoretic proofs, and this one isn't much different, but I figure we may as well prove something for the sake of proving something, because we're going to get into some pretty nasty theorems down the road. So lemma is that the inverse image of B under the relation R is the image of B under the relation R. Now, this statement looks kind of silly as written because it just says that two things are equal, and this is on purpose. Our image and inverse image notation line up nicely with the idea of an inverse relation to tell us that the inverse image of B under the inverse relation of R is the inverse image of B under R. So in order to prove this theorem, first note that the domain of R is equal to the range of R inverse. This is pretty much immediate. Again, we should be proving this maybe a bit more formally, but R contains those pairs which are x and y, as domain is the first coordinate, and inverse R contains, well, y and x, and the range is what's in the second coordinate. So these should line up. So suppose we had some x which was in the domain of R, then it's in the inverse image of B under R if and only if, and this is by definition of the inverse image, there exists some y in B such that x is related to y. But by definition of the inverse relation, this is only true if y is inversely related to x. In other words, x is in the inverse image of B under R if and only if x is in the image of R inverse, as we see in this last step here. Now, another thing we can do, of course, with functions, but even more generally with relations, is compose them. So suppose I had a relation S and a relation R. I could compose these two relations, and I simply define this to be the collection of x and z, such that there exists a y in the range of S, such that x is related to y, and y is related through S to z. And with that, we may as well come to the definition of function itself now. So we say that a relation f is a function such that if x is related to y and x is related to z, then it must be the case that y and z are equal. In other words, for each element of the domain of f, there exists a unique element in the range of f. And this recovers our familiar definition of function from, say, calculus, where we have a vertical line test. So this image would pass the vertical line test and be a function from the real numbers to the real numbers. Meanwhile, something that maybe did a loop-de-loop like this would not be a function because it does not pass the vertical line test. So this is just a more general version of the so-called vertical line test. Now, if f is related to y, we'll sometimes for y use the notation big F of little x. Again, this is just reflecting our calculus notation, or it may even be useful for us to treat it as a small index, so f sub x. And for functions in general, of course, probably seen drawing just an arrow between sets to represent a function f. But in this course, we're also going to get some functionality, pun fully intended, of using this angle bracket notation. So we denote a function like this. So we have f at a on the left-hand side with an a telling you what the domain is in the right-hand side in angle brackets, or even using f sub a with a subscript treating the domain as some sort of indexing set. So this is all just formal notation to mean a function, and recall that a function is just a binary relation, and a binary relation is just a collection of ordered pairs. So really, a function itself is just a set, but we typically think of it as relating the elements of one set to another. Now, I did mention that functions, we can define composition of them just as we can for binary relations, but we better make a formal check of this. So for binary relations, it wasn't too hard to see that just from the definition, of course, it's just a set of ordered pairs, so there's really not much to check. But with functions, there's a little bit more going on. So we're going to state this formally as a theorem, which is that given functions f and g, we have that f composed with g as a binary relation is in fact a function, where the composition g with f is defined at x if and only if f is defined at x as well, and g is defined at the image of f, the image of x under f. It's also worth stating that the domain of the composition of g and f is the domain of f intersected with the inverse image of the domain of g under f. And ultimately, this notation, g composed with f, applied to x, is the same as writing g of f of x. First, we want to show that g composed with f is a function. Well, we already know that it's a relation, but we want to show that it obeys a property if x is related to y and to z. That means that y is equal to z on the nose. So suppose that f is related under the composition g with f to some z1, and x is also related under the composition g and f to some z2. So by the definition of composition of functions, we know that there exists a y1 and a y2 such that x is related through f to y1 and y1 is related through g to z1. Also, that x is related through f to y2 and y2 is related through g to z2. That just comes from our very definition of composition of a binary relation. But now, since f is a function, we have x related through f to y1 and x related to y2. By definition of a function, this means that y1 is equal to y2. But then, looking at our g's, we have that y1 is related to z1, and we can now replace y2 with y1, so we have that y1 is also related through g to z2. But we've assumed that g is a function. So again, by definition, we must have that z1 is equal to z2, and that is in fact the result we're looking for to prove that the images are equal when the element of the domain is the same. And really, this second statement can be seen in some sense as a corollary of the third statement. So we know that x is in the domain of g composed with f, if and only if x is g of f, which is another way that we say this composition. X is g of f related to z, but that's only the case if x is f related to y, and y is g related to z for some y. But this in itself is only the case if x is in the domain of f, as we see it's on the left-hand side here, and y is in the domain of g. But y is also, under our notation, it's equal to f of x, and therefore, since it's the image of x under f, this means that x is in the inverse image of the domain of g. Therefore, x is in the inverse image of the domain of g, and it's in the domain of f, so we get the second part of our theorem. Now, when we invert a function, or a relation in general, we can always create the inverse relation, but if we invert a function, it is not always a function. Consider, for example, just the function from the real numbers to the real numbers defined by sending x to x squared. We know that for every element in the domain other than 0, it has two images. So, for instance, both positive 2 and negative 2 get sent to 4. So in the inverse function, there would actually be two different elements in the range with 4 as the corresponding element in the domain, which is not allowed for a function. However, if it is the case that the inverse of f is itself a function, in that case we call it invertible. And just like in naive set theory, we can define the notions of injectivity and surjectivity. So a function is said to be injective if for every pair of elements which belong to the domain of f, if the images of those elements under f are the same, then those original elements of the domain must have been the same. And surjective functions, which say that for each y belonging to the range of the function f, there exists some x in the domain of the function f, such that f applied to the element x is equal to y.
And of course we still have the notion of a bijective function, or which we call a bijection. And that, of course, is just when a function is both surjective and injective at the same time. So this basically will do it for now for us in terms of functions. There's a lot more to say about them, even at a very basic level. But in order to sort of see the more interesting aspects of this, we're going to move along and then revisit certain things about functions as we need them down the road. As always, questions, comments, concerns, you can leave them in the comment section down below, and we'll see you in the next video.